The quiz is very simple, all right? Very likely like the web assignment number 1 that I saw everybody finish, all right? So there are conceptual questions, and there could be a couple of basic calculation questions, all right? In quiz number 2, and and now that we're heading towards our first test, right? Oh, that will be later, but well, quiz number 1 is the 17th, quiz number 2, maybe the following week, or maybe Tuesday the 29th, and then I'm thinking about, because we will start doing Newton's laws by then, having a test at the beginning or mid-October, all right? So it will be a good idea, or it is a good idea, to apply some of the concepts of displacement, distance, vectors, scalars into some applications, all right? There you are. So that's what you have to do. All right. So I think that was my mistake, but that's okay. So let's take a look at this application, right? Very simple. So you have two semicircles. This one, let's say, is radius 2, and this one is radius 4. 4 meters, 2 meters. And let's start with an easy question. Let's say you're going from A to B following this path. All right? So you go like this. What is a displacement? All right. So the definition of displacement, we know it's a vector, right? We call it delta x, which will be position final minus position initial. So it's how far you are from the initial position. If we say this is 0, and that's your final position from A to B, then it's just what? All this. So your displacement for this problem is just basically AB. That's your displacement. It's how much you have moved, right? And I could say this is so if the radius is 2, this is 2 and 2, 4 and 4, 2 and 2 is 4, plus 4 is 8, plus 4 is equal to 12 meters in the positive x direction. Right? We don't care about the path. We only care about the distance between the person, where he was and where he is now, or she. Now, what is the distance traveled though? So, let's put here, what is the distance? The distance is the length that the person has traveled, right? So it's all this. So by that, we will need the length of this semicircle and the length of this semicircle. So let's find the length of that semicircle by using what? Well, this equation, if you ever need it, right? If it was in, let's suppose this was a homework question, right? I will have to give you the equation for the circumference. So here I will say, note the circumference of a circle right? If the radius is r, the circumference is equal to 2 pi r. 2 pi r is the circumference. So that's good. That means I can actually find that distance traveled. We have the circumference of this and the circumference of that. Those are semicircles. So using this equation, we can say that the circumference of a semicircle is equal to pi r. So for this one will be 2 pi. So the distance traveled is equal to 2 pi plus 4 pi. What's the value? 6 pi meters, no direction. You can leave it in terms of pi if you want. Right? So that's an example. I mean, an extension of that question. Right? If I want to extend this question, I can say this. If the journey took 6 seconds, what is the velocity and what's the speed? So we need our definitions of velocity. Velocity is the displacement over time, while the speed, the average speed, is the total distance divided by the time. So our velocity will be 12 meters divided by 6 seconds. That will give me 2 meters per second in the positive x direction. That's my velocity. And my speed, the average speed, will be the total distance divided by the 6 seconds here, right? So 6 pi divided by 6 equals to pi meters per second. So 3.14159, right? So the speed was greater than the velocity, right? Because of the difference between the displacement and the distance. Are there any questions about this? About the definitions of distance, displacement? No questions? You're good? So that's a nice example there, all right, where you can actually visualize the difference between distance and displacement. All right, so I call the class kinematics because today we're going to be doing more into the applications of speed, velocity, acceleration, displacement, distance. But I want to also do a problem on vectors that can help some of you that are trying to do the extra credit. So I'm going to call here extra credit, right? Because it will help you for that extra credit worksheet. And by the way, I have published another one, weekly problems number 2, and I will do problems that will help you for that as well. All right. Okay. So for the extra credit, you have problems. It's different numbers, but there is a problem, or there are a couple of problems, I believe, that are like this. So they give you the x and y axis, and they give you the, let's say they give you a vector here, 50 units, so 50, let's call it 50 for now. Another vector here. Yeah, let's put another vector here as well. But I want to change the value. So this will be 30, 30 as well, fine. But let's make this 40 and let's make this 10. So in this problem, let's say they want you to find the resultant of the vectors. All right? When they ask you something like this, you have to know you're given the angles, and you look at the magnitude of the vectors, 50, 40, 10. 50, you don't have to worry about in terms of like breaking into components. 50 is already in the y-axis, so that's good. But these two other vectors are making angles with the x-axis. So you want to find the components. That's what we did in the second class, I believe. We broke vectors into components like this. Same here and here. And yeah. So that allows us to find the resultant. All right. So what I'm going to do now is I will use that trigonometry. Now, since you guys have your calculator, you can always use that. All right. So you don't have to worry about memorizing anything of the trigonometric functions, but I want you guys to see how this works. All right. So let me actually see exactly how does the problem look. Yeah. So it looks exactly the same. All right. So let's see here if I can change a little bit these numbers. Yeah, no, that's fine. All right. That's fine. So this and that. 40 makes 80. So here we call it 40. That's the adjacent cosine 30. And here is the opposite. Opposite to 30 will be 40 sine 30. We do the same here. 10 cosine, 10 sine. 10 cosine, 10 sine. All right, we have this. And that's everything you need. I will write here what's the sine of 30. The sine of 30, you can use a calculator. Remember that it has to be in degrees, though. All right, is 1/2, so 0.5, and the cosine 30 is the square root of 3 divided by 2. So it's an irrational number. Now, so sine 30 is 1/2, so I have here 20, 40 times 1/2, and here I will have 5. So let's focus on the y-axis first. You have two vectors, one going up 20, another one also going up 5. So you have this. Two vectors, one with 5 units, one with 20 units, but you have a vector going down with 50 units. So 25 goes up, 50 goes down, the overall direction will be 25 going down. Right? If we have those vectors adding there like that. And on the x-axis, we have this one going to the right, this one going to the left. We do this minus this, and that's the solution for the problem. Right? We find the resultant on x and the resultant on y. So this is on y. And then, to find the resultant on x, we do, so here, on x, what we do? We do 40 cosine 30, so 40 times the square root of 3 divided by 2, that's to the right, minus 10 cosine 30, we have it there, and that will give me 20 root 3 minus 5 root 3. This is 15 root 3 to the right. And that's it. That's on the x direction. All right. Now you're probably thinking, can we get so that's the vector form. So this is the component on x, the component on y. Can we get a resultant? Yes. If we approximate 15 root 3, that's approximately, so for that, yes, you have to use a calculator. So it's approximately 26. So this is approximately 26. So the resultant will be the square root of 26x squared plus 25 squared. And that will give you the value for the resultant. All right. So that's the extra credit. That's how you do it. I believe the one in extra credit is easier because you have the same magnitudes. If they have the same magnitudes on x, they cancel, right? Because one is going to the right, is going to the left with the same magnitude, so they will cancel. You will just have a resultant on the y-axis. So this is more generic, all right? Just to see what happens when you have a problem like this. All right? Okay. So that was just to help you guys with those questions if you were to attempt those. So that was for week 1 problems. Week 2 has the motion problems. So I can show you the slides, but I'd rather show you the last set of slides on the board. What do I mean by that? I will show you how do we use distance, displacement, time, and velocity in graphs. All right? Because you can actually, and this is something that if you are doing the lab portion of the course, you will be doing that also in the lab. You will have to analyze a position versus time graph and a velocity versus time graph. So let's analyze. All right? The easiest one, I believe, is position versus time. So position versus time. How do you plot those graphs? You just have your, again, axis like this, but now here you will have your position x. It's one dimensional, right? It's the horizontal x, and here is your time in seconds. So let's suppose I'm gonna move. I start in position. So let's say where I am right now is position x equals to 5 meters. Let's say I stay here like this for 5 seconds. I'm not moving. So you draw a line for 5 seconds like this. That means that you are not moving. 5. But then I decide to move. I decide to move to position 10 meters in, say, 2 seconds. Like that. So now I'm in position 10, and it took me 2 seconds. So 5 plus 2 seconds, 7 seconds. And how much I move? 5 meters. All right. Then I decide to stay here for 3 seconds. So 7 plus 3, 10 seconds. And then I decide to, so I move here, I stay there, and then I will go back to my original position. So I go back here in, say, 5 seconds as well. So let's say something like that. So this will be after 5 seconds from 10, right? So I went back here. That would be 15 seconds, right? Let me introduce you to your position versus time graph. And you can have a lot of information here, like a lot. We will actually do a problem that I posted in the extra credit work there. You can get displacement and distance automatically, easy. You look at your final position. Your final position was this, and your initial position was here. So let's call this initial. They are also in, they both are in 5. So I can say that my displacement was 0 meters. Is that clear why? Right? Because your final position was the same as your initial position. But what will be the distance? The distance is not 0 because I moved, right? So first I was at 5. I moved 5 meters. I didn't move, and then I moved back 5 meters. So my distance is equal to 10 meters. How about that? Right? So that's a very neat way to explore motion and kinematics. Now, what other information I can get? I can get the average speed and the velocity during the whole trajectory. Well, I'm going to ask everybody, what would be the average velocity in the whole time? So between 0 and 15 seconds. What is the average velocity? Anyone? Think about it. What's velocity? What's the definition of velocity? Velocity is displacement over time. But how much is the displacement? 0. So my average velocity on that time is 0 meters per second. Is that clear? Right? It's all based on your definitions. Now, can somebody tell me what's the average speed? So let's put that in here. What is the average speed? The average speed is your distance, so we can call this speed. Oops. Is the distance over time. The total time is how much? From 0 to 15. If we simplify, we get 2 over 3 meters per second. Not bad, right? We found the average speed and the average velocity on the whole trajectory, on the whole time, on the 15 seconds. Again, another problem where you get different values, right? Okay. Now I will ask, what other information can you get? And this is very important. The other information you can get, guys, is you can get the velocities in each part of that trajectory. All right? For that, we will need to remember from Algebra 1, what's the definition of slope? The slope is the rise over run. But in mathematics, I mean, they tell you, yeah, delta y over delta x, and that's it, right? In some textbooks, they know, or they put as the first application this, all right? Why? Because in this case, the slope is your delta x over delta t, which is what? The velocity. So you need to know. All right? I can find the velocity here, and I can find it here, here as well, and here. When you have a horizontal line, you should know already from algebra, but if you don't remember, that's fine. For a horizontal line, the slope is 0. So the velocity here is 0. And here is also 0. But here and here it's not. All right? So what's the slope for this line? Rise over run. For this one will be also rise over run. But remember, right? Let's do it here. So let's see if you remember. A line that is opening like this has a positive slope. But a line that opens towards the left, so that has positive slope, but this line has a negative slope. So that's crucial. That's something that you need to remember. All right? To solve this anyway. The rise is what? From 5 to 10, 5. From 5 to 7, 2. So what's the rise over run? The velocity here is 2.5 meters per second. Now you're going from this point to this point. Rise is also 5. The time is now 5. So what is the velocity in this section here? Is minus 5 over 5 minus 1 meter per second. Look at all the things I found. I found the average speed, the average velocity, and the velocity on each section. Are you gonna be asked something? Are you gonna be asked something like this? Not really, right? What can I ask you though? This. To find this at least. That would be at least the basic thing that you need to know. All right, and you just have to look at the graph. The other thing is more further knowledge. It's important to know because it enhances your understanding of velocity and speed, right? And it uses some of the math, right? The concept of a slope. So at least that as an application, I think is a good idea to have it, all right? And it will help you for the extra credit. In the extra credit, I put a problem like this, okay? Position versus time. So that's what's in the slides, all right? In the slides, they give you every concept that I just talked about. It's in there, right? The position versus time, how you graph it, okay? And then in the lab, I believe you will be doing something like this. I want to erase this. I want to give it a few seconds. You might be writing this down, all right? But just to, before we continue, right? In the lab, you can have a particle or a mass or an object, and you're going to record the different positions across time. All right? So this one seems a bit more complex, right? but in the lab it's just one motion, right? Going to the right, for example. So let's actually show you how you will do something like that. So we still are position versus time. And in a lab environment, you will collect data of the position of a mass, right? As you use a time sensor, like that. So you will record this position, this position, this one here, right? You have probably more data points, so you will start from here, all right? What you need to do is, once you have the data points, you will use Excel. Excel is the best for this type of stuff. You will plot this, and then you will use a scatter plot, and it will give you something like that. And then what do you do with that? You have to pass a line. Like that. It's not going to be a perfect line. In Excel, you will try to fit it into a line, and you will find the slope. That slope is the velocity. And you know what? Because it's just going like this, and you just collect data in that direction, it happens to be also the speed. All right, but that will be your velocity in meters per second. All right, so that's what you have to do. That's the simple version of what we just did. Okay, so if you're giving a line with a positive slope like that, and by the way, the velocity will be positive, of course, right? It's increasing. You can also have situations where the velocity goes down. All right. So in that case, actually, sorry, it's not that it's going down. The velocity can also increase towards the negative value. That means it's going in an opposite direction. All right. Now, what we see here in these graphs is that in the position versus time, in these cases, the velocity was always constant, right, in a given interval. There is no acceleration. We haven't talked about acceleration in these graphs. Where will we talk about acceleration is in the other graphs, in the graphs of velocity versus time. So now, let's do the velocity versus time graphs. All right? And it's very similar. The only thing that you have to be careful is with the signs and the slope as well, right? So in a velocity versus time, right? You will have something like this. Again, you will use your X and Y axis. But now, this axis will be labeled V, meters per second. And that will be the time, seconds. Now, let's say you are going to be measuring an object that at the beginning is moving with 2 meters per second. So the object is here at 2 meters per second. And then it's going to accelerate towards 6 meters per second. And that's going to happen in approximately 2 seconds. right? Going from 2 to 6 in 2 seconds. Then the object is going to keep moving at a constant rate, constant speed for 4 seconds. So this will be 6. And then it's going to, again, increase the velocity. Now it's going to go more steep. Let's make it, actually, no, less steep. Let's go from 6 to 8 in 2 seconds. So this will be 8. And it went from 2 to 6 to 8 in 2 seconds. So this will be 8. And that's the final position, right? You can say that it continues at high speed, but we only care about that. All right. So what information can we get in a velocity versus time graph? In the velocity versus time graph, you can get the acceleration, the slope is the acceleration, which is measured in meters per second squared. What was the definition of acceleration though? That was the change of velocity per time, right? Now, I can get the acceleration in the whole trajectory, but normally we care about each section. As you know, here is horizontal, so the slope here is 0. That means that the acceleration there is 0 meters per second squared. I can get acceleration here, I can get acceleration here, right? How? By doing rise over run. In 2 seconds, the speed went from 2 to 6, that's 4. So the acceleration here will be 4 over 2, 2 meters per second squared. And here, in 2 seconds as well, the velocity went from 6 to 8. So 2. So the acceleration here will be 1 meters per second squared. I can get acceleration now. Right? That's important. If you want to go a bit further, right, I will show you now with a more simple graph that you can also get distance and displacement. All right. To do that, you will need to find the area under the curve. All right. If you compute the area under the curve, you can find the distance, and in that case, it's the same as displacement. All right, because it's all above the x-axis, so it's always going on one direction to the right. If you start seeing negative, like going below the x-axis, that's when you start seeing negative areas, and that's when the car or the object is moving to the left. But for now, don't worry about it. This is a more basic example, and I think that the general idea is that in the velocity versus time graph, you can get acceleration and the area under the curve. So let's write here the area under the curve or the graph is equal to the displacement. Slash distance. All right, so that's very interesting, right? So now we basically finished with that chapter of motion, with introducing these graphs. But that chapter does include a few applications. So what I want to do now is let's do the equations of kinematics. All right, I will write down the equations. I will do another graph just to show you where one of the equations come from, and then we'll do a couple of examples so you can see how to do that extra credit sheet. All right. This won't be on the exam on quiz number one. Don't worry. Quiz number one is very simple. It's conceptual. The same with quiz number two, right? But on the test, I might ask you a few things here and there, basic stuff, all right, which could be very helpful for also when you do your lab exercises, if you're in the lab, of course, right? All right, so let's introduce the equation of kinematics now, right? Because all motion, right, it's always characterized and modeled by the equations of kinematics. So let's put here the equations of kinematics. All right? For that, we start with the definitions. Kinematics. For constant speed, I don't think I need to be very explicit because only one equation. For constant speed, you have the velocity, and then we can talk about speed, but in this case, let's put it like that. We have the displacement over time is equal to the velocity, and then if we take the scalar, so if we take the scalar speed, distance over time is equal to the speed. That's just that one equation, right? The other name for this is uniform motion. Perfect. Things get more interesting when you have acceleration. So when you have acceleration, things get more interesting. That's when I would use this graph that I was talking to you guys about. Again, I'm going to use a velocity versus time graph. Seconds, meters per second. And then I'm going to go from this point to this point in some given time. From 0 to t. Let's call this V initial. And let's call this V final. For when there is a or accelerated motion or non-uniform, for a non-uniform motion, we define the acceleration as change of velocity, or in this case, the same speed per unit time. The equation will be V final minus V initial over time. So you can write the equation V final equals to V initial plus A T. That's your first equation of motion. We did that in the slides, right? That one there. We know that the area give you the distance, also in this case the displacement. They are the same in this case. So we can find that area of that trapezium, all right, trapezoid. What you will get is this, that the displacement or distance is equal to V initial times time plus 1/2 acceleration t squared. This is your second equation of motion. All right. Now, let's discuss what happens So we have those two equations now. Let's discuss what happens when the object is slowing down. When the object is slowing down, the acceleration is negative. So that graph won't look like this, it will look like this, right? Like that. The equations are the same though. It's right in general, so I want to put here in general. The final velocity or final speed will be the initial plus or minus acceleration time. You use a minus when the object is slowing down, right? And this guy also plus or minus. All right. And the final equation, when you combine these two, is that the final velocity squared is equal to the initial velocity squared plus or minus 2a delta x. That's another equation that we get. Those three equations are your equations of motion. And that's what you need for that extra credit for this week. Because it's all about problems on kinematics. All right, they are in Canvas already. Now, before we do some of these problems, you have to remember, right? The units for length, we've always been saying is meters, and we measure velocities in meters per second. But in real life, unfortunately, we do have a lot of situations where the velocity is measured in kilometers per hour or miles per hour. So how do you go from there to the other? So now we're going to do another exercise on change of units. And I'm going to give you a little factor to go from kilometers per hour to meters per second. All right? Let's do a few first. And then we're going to do a couple of exercises. And I think we can probably start introducing chapter 2 to finish that class. All right? So what you need to write down are just the equations there. All right? That's for non-uniform. Now, this is also very important. Conversion of speed units. So let's say I give you the velocity of an object 40 kilometers per hour on the positive y direction. We're gonna go, you're gonna convert this. So we're gonna change to meters per second. The way you're gonna do that is like this. You're going to do 40 kilometers per hour, and you're gonna be like 1 hour has how many seconds? 3,600 seconds. And 1 kilometer has how much? How many, sorry? 1,000 meters. That's called unit multipliers. Oh. Something happened here. Okay. Let's see. Okay. Right. There it is, right? Can you see the whiteboard clearly or not? Can you guys see the whiteboard, or is it too bright?
It is too bright, Professor.
Can you see it now? What about
It's
now?
still bright.
Let's see. There, can you see what's written there?
Further.
Let's see. Can you see that there?
Yeah.
Yeah? Let me know if it goes too bright. Then I will have to change the camera angle. Right now it's pointing towards the whiteboard. It should be okay now. All right. So, kilometers, hours and hours. So then look what happens, right? There. So you have 400, 40 times 10 is 400, divided by 36. All right. Now, if I divide by 4, it's 100. Divided by 4 is 9. So that's 100 over 9 meters per second. So that's how I change it. That's approximately 11, right? Meters per second. All right. So that's how you go. Those are the unit multipliers for to change the rate of to change the speed from kilometers per hour to meters per second. Now, let's see the factor that we have to use. The factor that I used was 1,000 over 3,600. So 1,000 over 3,600. Divide 5, divide 18. 5 over 18. So the multiplier to go from kilometers per hour to meters per second is 5 over 18. All right? That's the multiplier there. 5 over 18. So you can use it for any rate. If you have 36 kilometers per hour, then this is equal to 36 times 5 over 18. 36 over 18, that's 2. 2 times 5, that's 10 meters per second. All right? That's how you go from one to the other. All right? That's conversion of units for speed. And that's the most common one that you will see. Kilometers per hour to meters per second. For miles per hour, you will have to use the same, but remember that you will have to use miles. So 1 mile, let's see if you are interested, is approximately 1,600 meters. Because 1 mile is equal to, actually equals. You know why? Because 1 mile is equal to 1.6 kilometers. So the conversion will be that. So we greater, right? Will be greater than. All right, let's do a few of the problems then. Now let's do a few of these problems. I will show you where you can find them now. See this in here. And then here. So look, you don't have to do it like this, but something that helps a lot is to always do a drawing of the problem. You have a car that is moving at 60 kilometers per hour. And then after some, and it's accelerating, and then after some time, it will get to 90 kilometers per hour. Oh, that's much better, right? I think it was the illumination. Anyway, the acceleration is 2 meters per second square. So we use this. V final is there, right? Oh, V final equals to V initial plus or minus AT. It's accelerating, so we use plus. We have all the information, but we just need to convert. So 60 kilometers per hour, we multiply by 5/18. Right? That would be 300/18. That's approximately 17 meters per second. All right? I'm just gonna say that this has 2 sixteenths as well. There, and then 90 kilometers per hour, I multiply by 5/18. How much is that? That will be 25 meters per second. All right, so now I use the equation V final equals to V initial plus AT. I have acceleration, and then I can find the time, right? So 25 equals to 17. Yeah. Plus, what's the acceleration? 2 times time. Right? The acceleration there will be 2 meters per second as well. All right? So here, I subtract 17 on both sides. That gives me 8 equals to 2t. Right? So the time is how much? 4 seconds. Well, I round it. So in that case, we're pretty obvious what's the answer for that without rounding, right? So I rounded there. The 17 is actually 16.66. All right. I just did it to make it easier for the calculations, but that's the basic idea. All right. Any questions about this? Any questions about the formulas or the conversions? Okay. Let's actually give you guys a problem from here as well. I'll probably change the numbers a little bit and see if you guys remember what we did at the beginning. I will give you a position versus time graph, and then you will find a few things. I'll do it here as well. All right. Let's erase this. So with the position versus time graphs, remember that you can be asked a variety of things. All right. Actually, let's see. Maybe that will fix it. No. Maybe this. There. That's better, right? Yeah. All right. So let's do that. Now let's do the below the position versus time graph. All right. Okay. This is the problem. Let's see if you guys remember. So I'll give you very simple, huh? Position time. You start from the origin. You go up to 4. You let's do a memory stick. You keep going like this, and then you finish in 1. Oh. That's 1 there. The position is in meters, and the time is in seconds. That's your position final. That's your position initial. And they give you all the times. So let's say this happened in 2 seconds. And this happened in 4. Yeah. And this will be 6. Anyway, makes sense. Find the distance and displacement. Let's start with that. What is the displacement and what is the distance traveled? Much better. Now I know. So you have to turn on the slides here. Okay, so what's the distance and what's the displacement? This was the initial position, and this was the final position. Anybody? The final position was 1, and the initial position was 0. So what's the displacement then? 1 minus 0. That's 1 meter. That's it. Right? That's your displacement. And what's the distance? 4. So you move 4 meters. You stay in 4, so you didn't move. And then you went down to 1. So 3 meters. 4 plus 3, 7. See what I mean? That's your distance and that's your displacement there. Now, I ask, what's the average velocity and what's the average speed? Looking at the information that you have already there. Find the average velocity and the average speed. Anyone? The average speed, velocity, sorry, is related with the displacement. This. So the average velocity will be 1 over, what's the total time? 6 seconds. And the average speed is related with the distance. Way more. 7 times more than that. It's nothing weird. It's because one is a vector, so one cares about your direction of motion. The other one cares about just how much you move per unit time.